On the night of February 24th, 2026, astronomers around the world sat down at their computers and watched something happen that had never happened before in the entire history of astronomy. 800,000 alerts arrived in a single night. 800,000 separate detections of things in the sky that had changed, moved, brightened, dimmed, exploded, or appeared where nothing had been recorded before. All from a single telescope, all in a single night. All delivered within approximately 2 minutes of being detected. 800,000 reasons to believe that everything we thought we knew about monitoring the universe was about to change forever. And that was just the beginning. The Vera C. Rubin Observatory is not a telescope most people have heard of yet. That is very much about to change, because what this machine has started doing in the Chilean Andes is something that no instrument in the history of human astronomy has ever done before. It is not just taking pictures of the universe, it is watching the universe change in real time. It is building a movie of the cosmos, frame by frame, every single night for 10 years. And the images and discoveries it has already produced have left scientists struggling to find words adequate to describe what they are seeing. The story of how this telescope was built begins with a question. Not a question about any specific astronomical object or any particular cosmic mystery, but a more fundamental question about how astronomy itself should be done. For most of the history of the field, telescopes worked by pointing at a specific target and looking at it for a long time. You chose a galaxy, a nebula, a star cluster, a black hole candidate, and you dedicated precious telescope time to studying that one object in as much detail as possible. That approach produced extraordinary science. The Hubble Space Telescope's deep field images, in which Hubble stared at an apparently empty patch of sky for 10 consecutive days and revealed thousands of galaxies stretching to the edge of the observable universe, are the most famous example of what you can find when you look at one small piece of sky with enough patience and sensitivity. But that approach has a fundamental limitation. It can only show you what you choose to look at. Everything else in the sky at that moment is invisible to you. And the universe does not wait for you to point your telescope at the right place before something extraordinary happens. Supernovae explode without warning. Asteroids swing past Earth on trajectories that give a few days of notice at best. Neutron stars merge in cataclysms that produce gravitational waves and a flash of light visible across billions of light years for only a few hours. Black holes flare up as they consume nearby gas. Variable stars pulse in patterns that encode information about their internal physics. All of these events are fleeting. Miss them and they are gone. Unrepeatable, unrecoverable. The universe is not a static painting. It is a dynamic, constantly changing system that existing telescopes, by their very architecture, were poorly designed to monitor in full. The Rubin Observatory was designed from first principles to solve that problem. The Simony Survey Telescope at its heart has a primary mirror 8.4 meters in diameter, comparable to the world's largest single-mirror research telescopes. But instead of a small field of view like conventional large telescopes, it is paired with the largest digital camera ever built for astronomy, the LSST camera constructed at the SLAC National Accelerator Laboratory. The camera contains 189 individual charge-coupled device sensors arranged in a mosaic array, 3.2 gigapixels in total, nearly 3 times the resolution of anything previously flown in space or installed on any ground-based telescope. The camera's field of view spans 9.6 square degrees of sky, roughly equivalent to the area covered by 45 full moons placed side by side. In a single 15-second exposure, the Rubin telescope captures more sky than most conventional telescopes can cover in an entire night of observations. The numbers that result from combining that camera with that telescope and pointing the whole system at the sky every clear night are numbers that require a moment to absorb. In a single night of full survey operations, Rubin generates approximately 10 terabytes of data. Over the full 10-year legacy survey of space and time, it will produce a data set of approximately 60 petabytes of raw images, roughly equivalent to 60 million gigabytes, the largest astronomical data set ever assembled. Every image Rubin takes is compared automatically and in real time to a reference image of the same patch of sky. The comparison algorithm identifies anything that has changed between the two images, an object that has appeared where none existed before, an object that has moved relative to the background stars, an object that has brightened or dimmed. Each detected change generates an alert that is transmitted to astronomers and automated follow-up systems around the world within 2 minutes of the image being taken. During the single commissioning night of February 24th, 2026, before the full survey had even officially begun, that system generated 800,000 individual alerts, 800,000 detections of cosmic change in one night. Among them were detections of supernovae, the death explosions of stars massive enough to briefly outshine entire galaxies. detections of variable stars, whose rhythmic changes in brightness encode their physical properties, detections of active galactic nuclei, the brilliant cores of distant galaxies, where supermassive black holes are actively consuming surrounding gas and radiating energy across the entire electromagnetic spectrum, and detections of asteroids, hundreds of them, moving against the fixed background of the stars in the characteristic arc that distinguishes solar system objects from the stationary cosmos beyond. That asteroid detection capability is one of the most immediately practical aspects of everything Rubin does. In just 6 weeks of optimization phase observing before the full survey launched, Rubin discovered more than 11,000 previously unknown asteroids, including 33 near-Earth objects and 380 trans-Neptunian objects beyond Neptune's orbit. Near-Earth objects are the ones that planetary defense specialists track most carefully, because some fraction of them are on orbits that could eventually bring them close to or into collision with Earth. The Planetary Defense Coordination Office at NASA, which is responsible for cataloging and tracking near-Earth objects, depends on surveys like Rubin's to find the objects that current catalogs have missed. Before Rubin, the Catalina Sky Survey and other dedicated asteroid hunting programs were the primary sources of new near-Earth object discoveries. Rubin's discovery rate in just 6 weeks of pre-survey testing dwarfs what those programs could accomplish in the same period. At full survey rate, Rubin is expected to more than double the total number of known near-Earth objects within a few years. The scale of improvement over the best previous survey system is worth stating precisely. The Zwicky Transient Facility at Palomar Observatory in California was the gold standard of wide-field time-domain astronomy before Rubin came online. ZTF pioneered the rapid public alert approach that Rubin now uses at much larger scale. In its years of operation, ZTF discovered thousands of supernovae, hundreds of thousands of asteroids, and demonstrated the scientific value of surveying the sky frequently rather than deeply. Rubin can see objects approximately 40 times fainter than ZTF can detect. It generates roughly 10 times more alerts per night. Its camera covers more sky per exposure. Its survey cadence is faster. Every metric by which you would compare a wide-field time-domain telescope, depth, area, cadence, and alert volume, Rubin exceeds ZTF by an order of magnitude or more. It is not an incremental improvement on what came before. It is a generational leap. The full legacy survey of space and time officially launched on June 30th, 2026, after a period of optimization and careful operational review that the Rubin team described as ensuring every system was fully validated before committing to the 10-year cadence. Each night, Rubin is now collecting approximately 10 terabytes of data and producing as many as 7 million alerts of changes in the night sky. Those alerts stream to what the astronomical community calls broker networks, automated classification systems operated by institutions around the world that sort, prioritize, and distribute the alerts to researchers and follow-up telescope systems within minutes. A supernova detected by Rubin at 2 a.m. Chilean time can have a spectroscopic follow-up observation scheduled and completed by a telescope in Hawaii or the Canary Islands before dawn arrives in South America. The speed of the entire pipeline, from photons hitting the camera to alerts arriving at telescopes around the world, is measured in minutes, not days. The multi-messenger dimension of Rubin's operations deserves its own explanation because it represents something genuinely new in the history of astronomy. When two neutron stars collide somewhere in the universe, the event produces at least 3 distinct types of signal that reach Earth. First come gravitational waves, ripples in space-time that travel at the speed of light, and are detected by facilities like LIGO in the United States and Virgo in Europe. Then comes a brief burst of gamma rays, the most energetic form of electromagnetic radiation, detectable by space-based gamma-ray observatories. Then comes a kilonova, a brilliantly colored explosion visible in optical and infrared light that peaks within hours and fades over days. To study a kilonova fully, astronomers need to find its optical counterpart within hours of the gravitational wave detection and point multiple telescopes at it before it fades. Before Rubin, finding a kilonova's optical counterpart in the enormous patch of sky that gravitational wave detectors can only loosely localize was an enormously difficult needle-in-a-haystack problem. Rubin changes that calculation completely. Because it is already watching the entire southern sky every night, it will detect kilonovae in its regular survey data without needing to be specially pointed in their direction. The gravitational wave alert triggers a search of Rubin's real-time data stream. The kilonova, if it occurred in the southern sky, will already be in the dataset waiting to be identified by the broker software. The scientific goals that the legacy survey is designed to address are among the deepest in all of physics. Dark energy, the mysterious force or phenomenon responsible for the accelerating expansion of the universe, is the primary target of the LSST cosmology program by measuring the shapes of billions of galaxies across enormous volumes of space and looking for the subtle distortions that the universe's large-scale structure imprints on those shapes through a phenomenon called weak gravitational lensing. Rubin's data will provide the most precise independent measurement of dark energy's properties ever attempted. The Rubin commissioning analysis projects that after just 1 year of LSST data, its weak lensing measurements will reach precision comparable to the full survey results of the dark energy spectroscopic instrument, providing an independent confirmation or refutation of hints that dark energy may not be constant. That last point matters enormously. The standard model of cosmology treats dark energy as a cosmological constant, a fixed energy density built into the fabric of space-time itself. But recent measurements from multiple instruments have produced results that are in tension with each other and with the standard model in ways that hint at something more complex. If dark energy is not constant, if it evolves over time or varies from place to place, then the entire framework that cosmologists use to understand the universe's past and future needs to be revised. Rubin's measurements will either confirm the standard model or provide the most compelling evidence yet that something fundamentally new is happening in the physics of the universe at the largest scales. The timing of Rubin's full survey launch is not an accident in the broader context of observational astronomy in the late 2020s. NASA's Nancy Grace Roman Space Telescope, whose launch has been moved up to August 30th, 2026, will operate at the same time as Rubin's LSST for the entirety of its 5-year primary mission. Roman and Rubin are designed to be scientifically complementary in a way that multiplies the value of both. Roman operates in space, above Earth's atmosphere, giving it the crisp, diffraction-limited imaging resolution that ground-based telescopes, even excellent ones, cannot match due to atmospheric blurring. Rubin operates from the ground but surveys an enormous area of sky every night, building the wide statistical samples that cosmological measurements require. Together, they will provide both the depth of Roman's space-based imaging and the breadth of Rubin's ground-based survey, a combination that cosmologists designing the experiments of the 2020s specifically planned for when both telescopes were still decades from completion. The interaction between their datasets, Rubin finding interesting objects at scale and Roman following up the most important ones with exquisite detail, will produce cosmological measurements of unprecedented precision. The images themselves tell the story of what this telescope can do in ways that numbers alone cannot convey. The first look imagery released on June 23, 2025, when Rubin unveiled its initial data to the scientific community and the public in a ceremony in Washington, D.C., attended by senior officials from the National Science Foundation and the Department of Energy, showed the Trifid Nebula and the Lagoon Nebula, simultaneously in a single frame, 2 spectacular star-forming regions, several thousand light-years from Earth, captured together with a clarity and depth that required 678 separate exposures, combined over slightly more than 7 hours. Within those images, astronomers identified faint structures in the gas clouds surrounding both nebulae that had never been detected before, too faint for any previous ground-based telescope to resolve against the brightness of the nebulae themselves. In just over 10 hours of early test observations before commissioning was even complete, Rubin had already captured millions of galaxies and Milky Way stars and thousands of asteroids, a haul that would have represented months of observing time for any previous wide-field survey telescope. The Rubin Observatory is the product of more than 2 decades of work by over 2,000 scientists and engineers from institutions across the United States and from partner countries including Chile, France, Germany, and the United Kingdom. Its construction was jointly funded by the National Science Foundation and the Department of Energy's Office of Science at a total cost of approximately $800 million. That investment, spread over 20 years, is now producing a return in the form of discoveries that no other ground-based facility on Earth can generate at the same rate or at the same scale. The telescope sits atop Cerro Pachón, a mountain in the Atacama region of northern Chile at an altitude of 2,115 meters, where the atmosphere is so dry and so stable that the seeing conditions, the measure of atmospheric turbulence that limits ground-based telescope resolution, are among the best on the surface of the planet. It operates alongside other world-class facilities on the same mountain ridge, creating an astronomical complex that represents one of the densest concentrations of high-precision observational capability in the entire history of science. The woman this observatory is named after never saw it built. Dr. Vera Cooper Rubin spent decades in the second half of the 20th century making precise measurements of the rotation speeds of galaxies, sitting at telescopes on cold mountain nights, taking careful spectra of galaxy after galaxy, at a time when female astronomers were actively discouraged from using many of the world's major research facilities. Her observations turned out to be the most compelling early evidence for the existence of dark matter. If the visible matter in a galaxy, the stars, the gas, the dust, were all that existed, The outer regions of galaxies should rotate slowly relative to the central regions, just as the outer planets of the solar system orbit more slowly than the inner ones. Instead, Rubin found that the outer regions of galaxy after galaxy rotated at nearly the same speed as the inner regions, as if there were enormous quantities of invisible mass distributed through and around every galaxy she measured. That invisible mass is what we now call dark matter, and it is one of the two great unsolved mysteries of modern cosmology, the other being dark energy, that the legacy survey of space and time was specifically designed to investigate. Rubin received her data from cold, dark, remote telescopes and analyzed it on punch cards in an era when most of the Astronomica establishment did not take seriously the idea that a woman's observations could overturn fundamental assumptions about the structure of the universe. She was nominated for the Nobel Prize in Physics multiple times. She died in 2016 without receiving it. The Nobel Committee has never awarded the Nobel Prize posthumously. The observatory bearing her name, scanning the southern sky every night with the largest camera in the history of astronomy, finding asteroids and exploding stars and feeding the deepest questions in cosmology with data at scales she could not have imagined, is the kind of recognition that outlasts any medal. Rubin is bringing the universe to life, illuminating a treasure trove of discoveries including pulsating stars, supernova, explosions, the fossil record of galaxies, clues to the mysteries of dark energy and dark matter, and entirely new phenomena we have never seen before. That last phrase, entirely new phenomena, is the one that keeps astronomers awake at night in the best possible way. Every previous wide-field survey of the sky has discovered something that nobody predicted, something that fell outside every existing theoretical framework and required new physics to explain. The Sloan Digital Sky Survey, which mapped a quarter of the northern sky in the early 2000s, discovered the cosmic web structure of galaxy filaments and voids in greater detail than anyone had previously mapped. The Dark Energy Survey found evidence of tension in the cosmological model that remains unresolved. ZTF discovered the first known interstellar comet and dozens of unusual solar system objects whose existence had not been predicted. Each new survey found things the community did not know to look for. Rubin will observe more sky, more deeply, more frequently, and more systematically than any previous survey by a margin so large that the discoveries it has not yet made may dwarf what it has already found. The universe has been running for 13.8 billion years. The legacy survey of space and time is 10 years long. In those 10 years, Rubin will produce more data about more objects in more detail than all optical telescopes combined in the entire history of human astronomy. What that data will tell us about where we live, what the universe is made of, and what will ultimately become of everything we know is a story that has barely begun. The first night of real-time alerts was February 24th, 2026. The last night of the legacy survey will be sometime around 2036, and in between, every single night, this telescope will watch the universe change. Some of what it sees, nobody alive today can predict.